I now call to order the Society's 2,416th meeting in the 149th year since its founding on March 13th, 1871. Good evening, everyone.
Good evening.
My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Dean Romish in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW Science's YouTube channel. We will begin with a few announcements, followed by a reading of the minutes of the 2,415th meeting and the lecture by George Ricker on TESS, the Transiting Exoplanet Survey Satellite. We will then turn to this evening's lecture, followed by a question and answer period. When the Q&A session is done, I will present a thank you gift to our speaker, make a few closing announcements, thank those who make PSW possible, and adjourn the meeting to the social hour. Please join me in thanking the sponsors of the 2019-2020 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous sponsor who was asked to remain anonymous. Please also join me in thanking our sponsors of another type, the volunteers who've dedicated their time, expertise, and care to carrying on the Society's activities without compensation, serving science and the public, and maintaining almost 150 years of tradition of the Society. Especially join me tonight in thanking one of the members of the General Committee and the crew who keep this organization running and growing. A special thank you to PSW Recording Secretary James Heelan. James prepares and reads the minutes, keeping up a tradition going back more than a century, including accounts of the temperature, weather, and attendance. It takes a considerable amount of time, a good understanding of the subject matter, willingness to check accuracy, writing skills, and a scholarly disposition at the podium, with an awareness that what's written and the presentation will be available for reading and viewing in perpetuity. Thank you, James. We all appreciate what you do. We can applaud again. Should I leave you up? I'm pleased to announce that the following new members have been elected to the Society. Matthew Risco, a program business manager at NASA, interested in physics, astronomy, astrophysics, earth science, and space sciences and exploration, who comes to PSW through PSW speaker member George Ricker. Welcome, Matthew, and thank you, George. Sarah Ashley, a graduate student at Georgetown University, interested in, quote, all things science, close quote, especially biotechnology, who learned of PSW through a certain professor at Georgetown who will remain unnamed. That would be me. Demi Tilios, also a graduate student at Georgetown University, interested in biology and biotechnology, who learned of PSW through a professor at Georgetown. That would also be me. And tonight's speaker, Dean Romish, whose background and interests will be clear to you in part from tonight's proceedings. Please join me in welcoming them to membership. There is a signed reprint of Volume 1 of the PSW Bulletin for all new members. If you have not received yours, please see me and pick up your copy after the Q&A. And if you purchased a PSW ribbon, please see Savannah Crawford at the back and pick your ribbon up at the ribbon table. Recording Secretary James Heelan. Oh, dear. There we go. We'll now read the minutes of the 2415th meeting and the lecture by George Ricker on TESS, NASA's Translating Exoplanet Survey Satellite, delivered to the Society and guests on November 1st, 2019, right here in the Powell Auditorium. James, the podium is yours.
Thank you. Hi, good evening. As Larry mentioned, on November 1st, 2019, in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the 2415th meeting of the Society to order at 8:00 p.m. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. The minutes of the previous meeting were then read and approved. President Milstein then introduced the speaker for the evening, George Ricker, TESS Principal Investigator and Senior Research Scientist and Director of the Detector Laboratory at the MIT Kavli Institute for Astrophysics and Space Research. His lecture was titled, TESS's Exoplanets, Results of the Transiting Exoplanet Survey Satellite Mission. A transit is the geometric condition in which a satellite or planet passes in front of its host star. By constantly observing a star, scientists can detect transiting objects and infer their size and atmospheric composition. The primary goal of the Transiting Exoplanet Survey Satellite, known as TESS, is to discover transiting Earths and super-Earths orbiting bright, dwarf stars within 200 light-years of our solar system. The data TESS collects over its mission will be used to identify targets for further exploration by the James Webb Space Telescope, set to launch in 2021. Based on models constructed using the Kepler mission's narrow-view observations, NASA predicts that TESS's all-sky observations will identify 300 million stars and galaxies during the course of its 2-year mission. Ricker described TESS's cameras as, quote, exquisite photometers, acting as 64 million tiny light meters with a precision of approximately 30 parts per million, with a 2,300 square degree field of view, capable of observing approximately 6% of the sky at a time. He then described the sensors' technical specifications. One technical challenge was developing sensors that could observe stars cooler than our sun, which is approximately 5,600 degrees Kelvin. Approximately 80% of the stars in our galactic neighborhood are significantly cooler, ranging from 3,000 to 3,800 degrees Kelvin. To detect those cooler planets, TESS uses 4 special wide field of view CCD cameras with 105mm apertures and 24 degree by 24 degree field of view. Ricker described how these cameras were configured to fit into the SpaceX Falcon 9 rocket that, in April 2018, launched TESS into high Earth orbit. He then described the launch process and TESS's journey to reach final mission orbit, approximately 60 times the radius of the Earth, and the stability of that orbit. Ricker then showed images from TESS and explained how those images will be montaged together to produce a high-resolution composite. TESS has adopted an open data policy, and its data is being archived at the Space Telescope Science Institute. At current rates, TESS is set to distribute 10 times as much data as the Kepler and Hubble missions. Scientists around the world have already conducted follow-up observations based on TESS's data to detect 50 new planets with masses. And TESS is not only exoplanets. Ricker said TESS's full images could be used to study solar system objects, explosive and variable extragalactic sources, and variable stars. He described how TESS data has been used in the NEOWISE asteroid hunting mission to detect Centaur and trans-Neptunian objects, to detect supernovae light curves, and a tidal disruption event. TESS has already received a #1 ranking in NASA's Senior Review of Explorer missions, which, Ricker said, assures TESS of ongoing support to operate at least 4 more years. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the Society. At 10:05 p.m., President Milstein adjourned the meeting to the social hour. Temperature, 9 degrees Celsius. Weather, partly cloudy. Attendance in the Powell Auditorium, 93. And viewing through the live stream on the PSW Science YouTube channel, 29. Respectfully submitted, James Heelan, Recording Secretary.
Are there any corrections to the minutes or any comments on the minutes? If not, I will entertain a motion from a member to accept the minutes as read. Eric, do I have a second? I have many seconds. Therefore, the minutes are accepted as read and will be posted to the website in due course. We now turn to tonight's lecture on Argo, a flotilla of more than 3,500 autonomous free-drifting sensors deployed across the world's oceans, producing unprecedented measurements on their state. And it's my pleasure to introduce tonight's speaker, Dean Romish. Dean is Distinguished Professor of Oceanography Emeritus in the divisions of Integrated Oceanography and Climate, Atmospheric Science, and Physical Oceanography at the Scripps Institution of Oceanography, where he has been since 1981. He is a founder and leader of the Argo program and is coordinator of the U.S. Argo Consortium. Previously, he was chair of the International Argo Steering Team, and he led the original Argo design team. Dean served on the NOAA Climate Working Group, the Tropical Pacific Observing System Steering Committee, the U.S. National Academy of Sciences panel on sustaining ocean observations, and as a lead author on the fifth assessment report of the Intergovernmental Panel on Climate Change, to name just a few. He's carried out basic research on large-scale ocean circulation and climate for over 40 years. He's implemented many new technologies, and he has been a leader in designing, collecting, and analyzing new data sets on all of the world's oceans. He's a true expert on general ocean circulation and the role of oceans in the climate system, and a leader for many generations of the oceanography and climate science communities. He is an author on more than 100 research papers and has made innumerable presentations to professional and lay audiences. He is the recipient of the American Meteorological Society's Sverdrup Gold Medal and the Agassiz Medal of the National Academy of Sciences. He is a fellow of the American Geophysical Union and a member of the National Academy of Engineering. He earned his BS in physics from Swarthmore College and his PhD in oceanography from the MIT Woods Hole Oceanographic Institution Joint Program in Oceanography. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Dean to the podium. Dean.
Thank you, Larry, and thanks to all of the PSW members who've worked to put this together. I appreciate the opportunity to talk to you. I look forward to the discussion session that we'll have afterwards, and if you're not satisfied with the answers that I give you, I'd just like to mention that my UK Argo colleague is sitting in about row 6, and he's there to keep me honest. Came for the same meeting as I did this week, and so we can get a diversity of opinions if we ask Brian King to help us with that. So we're going to talk about Argo, and this is the way the talk will be structured. So first we're going to try to motivate. Why bother? Why take global ocean observations? What do we want to learn? And then I think it's really important to get some historical perspective on this program in order to understand how the subsurface ocean was measured before Argo. In fact, we'll go actually back 150 years, do a quick dash through the history of oceanography, and then how did this history give birth to the Argo program? How do these things called Argo floats work? What has Argo achieved in the 20 years it's been started and going? And then I'll branch out a little bit and talk about what else there is in large-scale oceanography, because Argo is not the only piece of what we're calling the Global Ocean Observing System. There are many other pieces, and what's of great interest is how these pieces fit together to answer some of the really difficult questions that we want to ask about topics like climate and global change, but indeed about many space and time scales in variability of the oceans. And then I'll end with saying, well, what's coming in the future of Argo that's going to be even more exciting. Okay, so why do we need these global ocean observations? Here is one familiar example. This is a graphic of the Earth's heat balance, and there are satellites measuring quite accurately the radiation at the top of the atmosphere. So so we've got about 340 watts per square meter of radiation hitting the top of the atmosphere, and about 100 of that is reflected, and another 239 roughly is re-radiated by the Earth as the Earth becomes something like a black body radiator. So if we add all these things up, we've got 240 coming down and 239 going back up. So that's a difference, a small difference of very large numbers, which means that in the face of uncertainties like you see in the small print beneath the numbers, which are more than well over a watt per square meter, we don't know the mean very well from the radiation measurements. The radiation measurements are pretty good at getting to the interannual variability, but not the time mean. So how then do we tell, how can we be sure that if the Earth's climate is indeed changing, if there is indeed heat being added to the system, if there's greater radiation going down than going out, how do we know? And the answer is that this is most accurately measured from temperature changes, and that goes for the ocean atmosphere and the cryosphere, but the ocean is the dominant piece in this puzzle. And that last figure came from the Intergovernmental Panel on Climate Change Fifth Assessment Report, and this figure is also from that report. This is then the energy accumulation in the Earth's climate system from temperature measurements. The units are zettajoules, so that's 10 to the power of 21 joules, and what you see is numbers that are in the few hundreds of zettajoules. And that simply comes from temperature. So the light blue, I may have got to get used to the system here. The light blue is now the upper 700 meters of the ocean. That's where 64% of the net heat is being stored. The dark blue here is the deep ocean, 700 meters and below. That's about 29% of the net storage. Everything else is about 7%, okay? Land is not good at storing heat. The cryosphere is not good at storing heat, and the atmosphere has too small of a heat capacity. It's good at mixing heat, but not at storing it. So almost all of the heat storage in the climate system ends up in the ocean. So if you want to know if the climate is warming, all you have to do is measure the ocean's temperature, but you've got to do it very carefully and very well. Well, so that's one reason, one aspect of the need for global observations, but I don't want to give you the impression that global change is all that this Argo program is going to do. So indeed, the uses of Argo data are quite broad. The graphic that you see here is the temperature anomaly at 100 meters depth in the Pacific in November 2015. That was the last major El Nino event. You can see the warm patch in the eastern equatorial Pacific, the cool patch further west. And so this data is very useful both for understanding what is the present state of the oceans and with respect to the El Nino cycle. It's also very useful for initializing models of the ocean that will run the coupled ocean-atmosphere system and lead to better predictions of El Nino. So there's a host of research topics that require regional and global ocean observations. This includes looking at water mass properties, water mass formation and its variability, ocean circulation, including boundary currents, interior flows, meridional overturning cells, mixing, mesoscale and submesoscale variability, air-sea interaction, salinity in the hydrological cycle. The list kind of goes on. And this is simply because by measuring everywhere, you get sort of the bread and butter of what's needed for oceanographic research. Okay, so let's wind back history 150 years or so and look at the beginning of global scale oceanography. And this was the Challenger expedition of 1872 to 76. And here's the Challenger, HMS Challenger. It was a converted British warship made into a research vessel. So some of the cannons were replaced by, labs and flower pots. And Challenger made a global survey. Whoops, I knew I was going to do that. Challenger made a global survey. It went along these red lines in all three oceans. And it had a number of objectives. But one of these was to look at the basic stratification of the ocean. Before Challenger, we didn't know that the ocean was stratified globally in a way that looked something like this. This is actually from Challenger data on a line between New York, Bermuda, and St. Thomas. And this is really very similar in structure to the ocean today. There's the Gulf Stream is here. There's a large water mass called subtropical mode water here. There's a sharp thermocline, that is, we go from warm temperatures at the sea surface to cold underneath. By the time you're down to 22,000 to 2,500 meters, the global ocean is relatively more uniform and something like 3 degrees C. So that was all unknown before Challenger. The basic stratification was really learned by that expedition. And this is the instrument that was used to measure that stratification. It's what's called a minimum thermometer. It's much like the thermometer that you would put in your garden overnight if you want to know how cold it gets to be at night. It's got a mercury column that pushes against a little index, and so where the index stops is the temperature minimum seen by that thermometer. So as long as the ocean goes from warm to cold as you go down, then you can lower a string of these minimum thermometers and they'll just record for you the temperature at whatever depth the lowering stops for that instrument. And the Challenger had enough hemp rope to sample all the way to the ocean bottom, so they would simply put a string of these thermometers onto the rope and lower it down to the bottom and get a profile of temperature in that way. Okay, winding forward, so what was missing from the Challenger. Actually, the Challenger had a few of these, had some water bottles that were experimental at the time. They didn't use them extensively. Challenger made about 300 stations worldwide. That is, there are 300 locations where strings of thermometers were lowered down to the sea bottom to record the temperature stratification. So reliable water bottles came along later. This thing is a Nansen bottle, and the idea was you would clamp this onto the steel wire being lowered by the ship's winch. So here you see the Nansen bottle clamped at both ends, and when it's upright like this, the bottle is open at the end so water can flow through it. You put a whole string of these, perhaps 25, onto the wire, and then you send what's called a messenger, which is just a weight clamped onto the wire, but it slides along the wire. The messenger comes down, hits the release on the top of this Nansen bottle. The top clamp lets go, and the bottle inverts. When it inverts, it also closes the ends, so the water is trapped inside. And the now precision deep sea reversing thermometer, which looks like this and is inside this part of the bottle, that's flipped upside. Whoops, I've done it again. The thermometer is flipped upside down as well, and it has a narrowing of its mercury column in it, so that mercury breaks off when the thermometer keep doing it, when the thermometer flips, and so it traps the measurement made by the thermometer at that depth. The water samples were at that time mostly for measuring salinity, and I'll come back in just a second to how salinity is measured. So Nansen bottles came into use around 1910. Deep sea reversing thermometers were then and are very accurate to about a few milledegrees, a few thousandths of a degree C, very carefully calibrated. And the depth from these casts was calculated in a relatively clever way using a pair of reversing thermometers, one of which is protected from outside pressure by a glass sheath, and the other which is not protected. And so the difference between those two measurements gives you the squeezing of the unprotected temperature by the ambient pressure. And so from that temperature difference, you can calculate the depth of that water bottle when it was triggered to within about 5 meters. So these were great tools, but in order to use them, you needed research vessels. And during the 1920s, 3 major ocean-going research vessels were commissioned. That included Woods Hole's RV Atlantis, the German Meteor, and the British Discovery. All of these were commissioned in the 1920s. They all made ocean-scale surveys, unfortunately all in the Atlantic. And what you see here is a map of all stations that had ever been made to depths at least 2,500 meters by the year 1935. So it's a very sparse sampling of the Atlantic. The sampling of the Pacific and Indian Oceans was, dare I say, much sparser, but I think you get the idea. It took a lot of effort to get a large ship out there, and the collection of data was quite tedious and time-consuming. Okay, salinity. So why is salinity important? Well, the density of seawater, and hence the physical dynamics of ocean circulation, is a function of salinity as well as temperature. So in order to know the density of seawater, you need both temperature and salinity. Furthermore, salinity is a great tracer to be able to follow waters that sink in places where there's either excess of evaporation or excess of precipitation. High precipitation areas give rise to low salinity water masses that can sometimes be tracked for a long distance, and the same is true for the evaporative regions, giving rise to high salinity. So salinity is very important, very useful, and up until the 1950s, it was measured by chemical titration, which was quite slow, not terribly accurate. So with some experimentation, this salinometer, electronic salinometer, was created in the 1950s, and this was to determine salinity from conductivity, and the way that it works is to take a sample of known conductivity or known salinity and find the ratio of the conductivity of the salinity sample you're trying to estimate with the standard seawater, and get this conductivity and salinity that way. So the figure on the right is just a modern guild line autocell. Basically, this follows the same principle as the original salinometers, but does so in a little more compact and more accurate way. What you see here is a bottle of the standard seawater that's used to calculate the conductivity ratio. So there was quite a cottage industry, or probably, and there still is, I think, for creating the standard seawater of known conductivity and salinity. So still moving forward in time now into the 1960s, I think everyone reckoned that, well, since we can measure conductivity and salinity electronically, let's do it all electronically. And this early instrument for doing it all is shown here. So this is a conductivity temperature depth recorder, or CTD as they're called, in the late 1960s. And these were refined over the next couple of decades into very accurate instruments. The early ones didn't work that well. They certainly didn't replace things like the high precision temperature, deep temperature measurements for quite a while. So now into the 1980s, when the CTD measurements of high accuracy started to become routine, and the sorts of accuracies that we're talking about are 2 millidegrees in temperature, about 3 parts per million. So salinity of seawater is about 35 grams of salt per kilogram of seawater. Here we're talking about 3 milligrams per kilogram of seawater. So it's a very small error bar on the salinity, and still pressure to about 5 meters. But these started becoming routine in the 1980s. The Nansen bottles were tended to be replaced by this battery of Niskin bottles. They're somewhat similar, but these are now electronically closed at their ends with a signal sent down the wire. The CTD rests pointing down, so it gets clean seawater coming through this instrument package. And these might have, these rosettes might have 24 or 36 Niskin bottles on them. So the idea was then floated and agreed that a global survey was needed now that these tools were refined to the extent that they were, and now that it was fairly well known that the oceans had roles in the climate system. So this survey was designed and carried out in the 1990s, 1991 to 97, the World Ocean Circulation Experiment. This is the only global survey, top to bottom, ever carried out. It was quite expensive. but there are still some ongoing. A subset of these lines is done on approximately a decadal basis to look at long-term change along a few of these lines. So this is a great technology. The only drawback, a research vessel had to be present. Takes about 4 hours for a deep station. You have to typically steam for 4 to 6 hours in between stations. So it's a fairly slow and fairly expensive business. So in parallel with the advancement of these water sampling, temperature, salinity kinds of measurements, there were also a number of moves in oceanography to try and reduce the dependence of ocean measurement on the research vessel because the research vessels were so expensive. So this began with the effort of John Swallow, an iconic British oceanographer who's shown here. He's being carefully watched by this cat, and he's got long pipes which he bought at the hardware store. They're sealed off at the ends, equipped with an acoustic sound source inside, and very accurately ballasted so that they're just a little bit heavier than seawater at the sea surface. And once they sink to a predetermined depth and they encounter denser seawater around them, then they become neutrally buoyant and don't sink anymore. So these things will sink and then drift with the current and go make a pinging noise as they go that can be picked up by the ship's hydrophone. So these things, known as swallow floats after John Swallow, they were tracked by driving around, driving the ship after them. So we haven't saved too much ship time yet, but still it's a fascinating idea and the first of the autonomous floats that had been invented. So now here's a real, talk about cumbersome. Here is a similar instrument, but now this has been designed to be tracked not by a moving ship, but by a stationary mooring. It's a sound source. You can see down here two of the individuals who developed this instrument, Doug Webb and Tom Rossby. So these are 6 feet tall. This thing is quite large, therefore, and it's basically an organ pipe, makes a loud noise that can be heard from hundreds of kilometers away. If you have 3 moorings out in the ocean, you can track the acoustic signals and triangulate the position of the float. So these were now, you needed a ship to deploy them. The moorings are fairly expensive, but nevertheless, now we're starting to get autonomous. These were tracked at long range by the moored hydrophones. And then these were called SOFAR floats because they floated in something called the SOFAR channel, sound fixing and ranging sound channel. The next step in this was to reverse the roles of the moorings and the floats. So the floats got to be much smaller. They became the data recorders. The moorings were the large sound sources. So basically they just flipped the role of float and mooring. And so that was, if you flip so far, you get Rayphos. So that's a Rayphos float. And these are still deployed to some extent today. Okay, now you've been waiting for this. Here it comes. So this is now the Argo era starting to come on into view. So Doug Webb and Russ Davis, my colleague at Scripps, decided, well, instead of tracking these things acoustically, we'd like to track them by satellite. That way we can deploy floats anywhere in the world. And so that's what this thing is. It's an instrument that can control its own buoyancy. I'll show you a schematic in a minute. So it can go from the sea surface down, say, 1,000 meters, drift for, say, a month, and then come back up to the sea surface, and the difference between the satellite position where it went down and the satellite position where it comes up, that's the flow at 1,000 meters. So this was a very prolific instrument during the World Ocean Circulation Experiment. Several hundred of them were deployed, and sort of halfway through that exercise, Webb and Davis decided, well, we might as well put a CTD on top. Why just measure ocean circulation? You can measure temperature and salinity as well. And then that gave rise to an instrument which was virtually identical to today's Argo float. So you see several photos of those, and just for comparison, this is actually a closely related instrument called an undersea glider. It's just a profiling float, has the same buoyancy control system in it, but it has, as you see, wings and a tail. It has a compass. It has batteries that can move forward or back in order to change the angle of attack. So this thing you can tell it where you want it to go. It's a great instrument for sampling the ocean margins, even as Argo floats are great for sampling the ocean interior. Okay, so this is more precisely what an Argo float does. It descends from the sea surface to 1,000 meters and drifts there for about 9.5 days, descending further to 2,000 meters, and then immediately coming back up to the sea surface, where it reports using iridium cellular communication. So this float has a cell phone in its pocket, and it sends its data back as text messages. So these things are texting away. They send back about 3 kilobytes every time they surface. They stay on the surface for only about 10 minutes. So the sea surface is where all bad things can happen to instruments, so it's good to get away from it as quickly as you can. And this is now the insides of the instrument. The heavy stuff is down at the bottom to keep it upright. So the batteries, lithium-ion batteries, are down here, and the hydraulic pump, which can push mineral oil from this interior reservoir down to a bladder which is on the outside of the float beneath it. So by moving mineral oil from one reservoir to the other, you can either make the volume of the float larger, in which case you've increased its buoyancy and it goes up, or you make the volume of the float smaller, decreasing its buoyancy, and it goes down. So that way you can go between the sea surface and 1,000 or 2,000 meters, and you can do it repetitively as often as you want. This is a much more economical way of collecting this bread and butter CTD data from the oceans than if you use a research vessel. The cost of an Argo profile is roughly $200. The cost of a shipboard profile, if you add in the ship time, is over $10,000. So it's quite economical by comparison. So Argo was really created by, if you like, the combination of the technology advancement which had happened around us and the desire, the scientific need for global ocean observations. And so a number of people got together. I don't know exactly who this is, but we knew that we needed a global ocean observing system to look at climate variability in the ocean. And we could see that this profiling float was just the instrument to do it. So this was a made-up map, I know because I made it up, showing what we had in mind. So a global array of about 3,300 profiling floats. measuring temperature and salinity in the top 2,000 meters of the global ocean and repeating it every 10 days. I think the scientific consensus for Argo was achieved by going out, talking about Argo at a number of different forums, including the World Climate Research Program's CLIVAR project and the Global Ocean Data Assimilation Experiment. Good day. And one of the main selling points for Argo was its synergy with satellite observations, such as sea surface height. We'll see more of that in a minute. At the same time, these things cost real money, and we succeeded in the U.S. in training the assistance of NOAA. Jim Baker was the administrator of NOAA at that time. He and the chief scientist, Stan Wilson, were enormously helpful in not only in getting Argo off the ground with U.S. funding, but also in training their partner agencies in countries around the world. And so that is why Argo is today. It's a multinational program with about 30 international partners. And here you see Stan Wilson discussing with George W. Bush the Argo project in 2002. So that's what got it going. It was this parallel scientific consensus and agency encouragement. Floats were started being deployed in the hundreds, and we reached the target of 3,000 or 3,300 floats in late 2007. Since then, it's gone up a little higher, and today there are about 3,850 Argo floats out there. So I ask you, I guess, how do you think we did? Does this picture on the right look sufficiently like this picture that it looks like we've more or less done what we said we would do? The figure on the right here just is the same information, but in the form of the number of floats per 6 degree by 6 degree box. There's intended to be one float every 3 degree by 3 degree box, so these boxes should contain about 4 floats. If you see light green or medium green, they're just about perfect. Dark green is a little bit oversampled. Orange and red mean undersampled. So we're still not, this is this year, this is just recently, August 2019. We're still not doing great in the Southern Ocean, and that's for lack of deployment opportunities. There just isn't, we're not getting enough shipping traffic to do a better job, but I think, I hope we will in the future. Some of the marginal seas are also not perfectly sampled, such as the Southeast Asian seas, as you see, which show up as red. In the figure of 3,850 float locations, each of these colors is a different national program. So dark green is the U.S. Argo program, and the U.S. is doing about half of the total number internationally, but you can see other prominent programs showing up in different colors, and if this was blown up enough, you could read the national contributions. But I think the major contributors are mostly, as you would guess, European countries. The UK and France are very active. Australia is very active. India is very active. China is very active. And there have been over time about 30 contributing countries. Argo could not be done by any country alone. We could not possibly cover the whole ocean just with the resources available in U.S. Argo, but we do try and guarantee the global spread of the floats by taking responsibility for areas where many of our partners are not able to deploy floats. here's another way of looking at the whole of the Argo data set and how it differs from what came before. So Argo at this point has collected 2.14 million temperature salinity profiles, and this is the density of profiles in 1 degree boxes. And the median number here is 50, so 50 profiles every 1 degree by 1 degree box. And the plot down here, this is the accumulation of all temperature salinity profiles in the history of oceanography before Argo. Again, it's in 1 degree boxes. There are large blank areas where there have never been any stations, so that's unexplored territory. The whole of the southern hemisphere is very lightly sampled, and really most of the profiles are near coasts and in the northern hemisphere. So this is the difference that Argo has made in our ability to sample the ocean. This is roughly 15 years worth of Argo profiling. This is 50 years worth of profiling by research vessels. So the idea behind Argo, I think, is systematic global ocean observations. We wanted a subsurface observing system that is satellite-like in its space-time coverage. The historical data set is also very sparse in winter. It's wintertime measurements. And so here you have all of the 1,000-meter temperature salinity profiles ever made in the month of August. It's wintertime in the southern hemisphere, and research vessels don't like going to sea very much in the winter. Profiling floats don't mind. Argo floats are happy. They don't get seasick. They're not bothered by large swell and wind, and this is five years only of accumulated Argo profiles in the month of August. Okay, so how did Argo succeed? People always want to know, what was the secret? How did it happen that the program managed to do what it does and to keep on doing it? And one of the secrets really is that the technology has not stagnated. We're still making floats that are better, that have more capabilities, and that will live longer. And the live longer is illustrated here. This is a survival rate, percent surviving as a function of time in the water. So here we are at 4 years. So in the first 5 years of Argo, almost all the floats were gone by 4 years. By the time you got to 2014 to 2018, about 60% of the floats are lasting for longer than 4 years. And still, some of the groups are doing better than others. I say this because so I can brag a bit about the Scripps contribution. This is SIO Argo floats between 2014 and 2018, and over 90% of those are lasting for 4 years or longer. We're still making advancements. These have been due to cutting the amount of energy used by a float, to using improved battery technologies. Telecommunications, the use of iridium is much more economical than what came before it. We're better at testing and designing floats. We're better at shipping them, and we're better at deploying them. So they do last longer. Another secret, really and truly, is international cooperation. There's something called the Argo Steering Team and the Argo Data Management Team. These coordinate the float contributions from all of the national programs, plus the logistical assistance of many others. So these really are the glue that holds the International Argo Consortium together. And the next thing I would mention is Argo developed a very revolutionary at the time comprehensive data management and float tracking system that have certainly contributed to the viability of the program. Finally, Argo could not succeed if the user community didn't think it was worth having. So developing, supporting high-value applications has always been at the forefront. And here you see the number of research papers each year that have used Argo data. We keep a complete bibliography. You can find this on the Argo website. And it's gotten up to about 400 research papers per year. So every day, 7 days a week, 12 months a year, there's another Argo paper that's written and published. And these have addressed, as I indicated earlier, a very broad mix of research objectives. Argo is really gaining in education programs, and a number of nations have developed programs to utilize Argo data and to use it to allow students to explore the world in Argo data. And last but not least, there are many operational centers that run modeling operations to do ocean reanalysis or short-term forecasting, seasonal to decadal prediction. Argo is the bread and butter of these operational applications, and they're finding the data set very valuable, and it is the key for their success. There are challenges for sustaining the Argo program. There's a very high demand on the limited national research budgets that sustain the program. We don't really have a comprehensive method for deployment strategy, but we have found that we can deploy most of the Argo floats using opportunistic vessels, chiefly research vessels that just happen to be going on long voyages, and we use all of them, but there just isn't enough traffic either in the South Pacific or the South Indian Ocean. So we've developed a collaboration with Australian Argo and New Zealand Argo to use this very small research vessel to deploy about 100 Argo floats a year in the most hard-to-reach, remote pieces of the ocean. And what you see here is a map year by year of all of the Argo floats, all 1,700 Argo floats that have been deployed by this research vessel, Kaharoa. And so going forward, we're going to have to keep prioritizing technology improvement and better data management to reduce the systematic errors in the data set for global change studies especially, and to avoid or identify any major technical failures that are coming at us. So before starting to wrap this up, I wanted to come back to the point that Argo is one element of the global ocean observing system. So tell me some more elements, okay? There is repeat hydrography, so this set of lines is the subset of WOS sections that are repeated approximately every 10 years. So these are research vessel transects. They make the highest possible quality data set. They're used for reference data for Argo, we think that they're extremely valuable because of the high data quality that they offer. So repeat hydrography, and that program is called GOSHIP. The expendable bathyc thermograph is an interesting instrument that I failed to include in my little brief history. Here is a person deploying an expendable bathyc thermograph. It was developed, came out of World War II, where there was an earlier version of this. These things have a tiny copper wire that connects the launcher here to the probe that you see dropping out here, and they can collect about 700 meter profile of ocean temperature. there are two spools of wire, one in here and one in the probe, and they both pay out at once, and that's how you can use a very thin wire and not have it break immediately. So a lot of XBTs, as they're called, have been deployed, and this map on the right shows that same distribution diagram for XBTs. So this saves on research vessel time. You can deploy these from commercial ships. You have to have a ship, but it doesn't have to be a research vessel. And 500,000 XBTs are shown here, deployed in the decade from 1995 to 2005. Other elements of global observing: sea level gauge network, which you see here. All these dots are carefully measured sea level. Gliders, I showed you what a glider looks like. There are networks of gliders operating across the ocean's margins. Surface drifters that can contain useful instruments like barometers to aid weather forecasting. And then there's a host of satellites for variables like sea surface height, ocean mass, wind stress, sea surface temperature, sea surface salinity, top of the atmosphere, Earth energy balance, and even others. So how do we put these things together? I think, how do we get the real value out of integrating this ocean observing system? And here is one. So this is another figure of the heat balance of the planet. And what it shows is, so this is the upper 700 meters here, and this is 700 to 2,000 meters, and each of these lines is a different agency's interpretation of the global data that's available as a function of time. So this runs from 1995 to the present, and you see that there's a lot more scatter when the XBT data set and the GoShip data set were all that was available. Once Argo came online around 2006, the error bars grow much smaller. And the same is true in the 700 to 2,000 meter range. So if we looked at, the temperature changes over this period of time, 1995 to 2005, it would be difficult or more difficult to argue that there's actually a warming trend, because the error bars were nearly the same size as the trend for that first decade. That is no longer true, and the data set is much longer in time, and the measurements have become much more accurate because of the coverage gains of the Argo program. From GoShip, we can also add an estimate of what's going on below 2,000 meters. There is a small but significant warming signal there as well. And this now is the trend as a function of depth over this period of time in degrees C per decade. So the surface layer of the ocean is warming at tenths of a degree per decade. There is warming seen all the way down to 2,000 meters, but it decreases in magnitude to hundredths of a degree per decade. But this is far below the error bar of, far above the error bar of the Argo data set. And I mentioned that the Earth radiation budget does a good job in interannual variability. Sorry for the quality of this figure, I didn't make it, but it compares Earth radiation heat gain in the climate system with that from Argo. And I think you can see that I hope you can see that the two lines track each other fairly well at the end of the data set, not at all well at the beginning. So this is before Argo and then after Argo. And as I said, they're not doing the mean very well. The mean has been adjusted so that they agree, not taken from the data. But the interannual variability tracks very well. It's a good confirmation of the quality of the data of both data sets. Sea level change is another very interesting topic that requires multiple elements of the observing system. So sea level, net sea level change is measured quite well by the combination of satellite altimetry and coastal sea level gauges. That's the black line shown here. The mass of the ocean, so sea level change is due to changes in ocean mass and changes in ocean temperature. Change in ocean temperature expands the water so that it makes sea level rise. The mass component is larger in the global mean. And here you see in dark blue is the mass contribution, which is also measured by satellite. And then from Argo data, the so-called steric contribution, that is the expansion of the ocean due to changes primarily in temperature, are shown here. And the interesting thing now is if you take the red line and the dark blue line, add them together, you get the purple line, which, as you can see, matches the sea level change record very accurately. So I think this is a very important part of doing this sort of research. You need to close the budgets. You need a degree of redundancy in the budgets. You don't want to estimate things as residuals, and you have to guard against systematic errors. And this figure is from the bulletin of the American Meteorological Society, which puts out a yearly state of the climate, and you can find this in the latest edition. Okay, what is in Argo's future? So first, well, you know, we've only been measuring to 2,000 meters. And we only did that because that was the limitation of the profiling float technology that you've seen. The CTDs were not accurate enough for the deep ocean, which has much smaller signals. The float themselves had aluminum pressure cases, which couldn't go to 6,000 meters. So early on, Argo has been limited in that way, but we've always wanted to go deeper, and now we have the floats to do it. This is a deep solo float developed in the float lab at Scripps. Here I am bragging again. And there are 3 other floats developed one in the US, 2 in other nations, that also take Argo into the deep ocean. We know that there are seasonal to decadal signals in temperature and salinity and in ocean circulation that extend all the way to the bottom. So we're trying to illustrate that and prove it and, in fact, extend the Argo array to the ocean bottom. There are presently 96 deep Argo floats operational at depths up to 6,000 meters, with 65 more planned in the coming 6 months. So the concept here is to have deep floats, something like this. What this really means is to convert about 1,250 of the conventional Argo floats into deep ones. And this graph is keyed by nations. The green dots are U.S. deep Argo floats, and the other dots are other national contributions. So again, I think we're going to have a robust multinational group in order to execute this program. And so now we can really close the budgets. You know, with those lines I showed you before, one could ask, well, how much are you missing by not having the deep ocean? Well, we can shut that door. And also, if we look regionally, the signals and the trends are much larger and have much greater projection into the deep ocean. The other big news in Argo is the development of biogeochemical sensors. So why shouldn't Argo be a multidisciplinary array? Why should it just be physical measurements? There's a huge enthusiasm for doing this out there in the world. There are three models so far of biogeochemical Argo floats. This map shows the location of all the BGC Argo floats presently active. About half of them, I believe, only have dissolved oxygen, but the intention here is to actually measure 6 different parameters from these floats, starting with dissolved oxygen plus pH, nitrate, and biooptical properties for ecosystems health. So the pH will tell us about ocean acidification, the oxygen about deoxygenation. Oxygen is decreasing, especially in the low oxygen regions that are out there. So I think this conversion of 1,000 regular Argo floats to BGC Argo floats will have great and interesting results. So just to put an idea out, maybe get a few people interested, anyone can explore the Argo data set. Argo data is immediately available in near real time, and anyone can get it on the internet. Don't even need, no password needed. No contribution needed. You don't have to buy floats, but it would be nice if you did. So anyone can explore the Argo data set. Everybody can get the data just as promptly as I can. They can write the paper before I get around to it because I'm too busy worrying about the next Argo float. And here are just a couple examples. So Argo samples the world ocean in 4 dimensions: latitude, longitude, depth, and time. And this is a vertical section, so the y-axis here is depth in meters, and this is latitude from 60 south to 60 north. This is temperature. You're seeing that basic stratification of the ocean and how it varies quite a bit with latitude. And wherever you see slopes, and you see them everywhere, that's indicative of ocean currents. This is the Antarctic circumpolar current showing up in the temperature field. This is salinity, and remember I said that if you have a highly evaporative region like you have at 30 degrees north or south, and here's 30 south, high salinity water descending from the sea surface and flowing equatorward, and that reveals much about ocean circulation, about air-sea exchanges, about water mass formation and spreading. Just for fun, here's a slice on different axes. So we're still looking at depth, but only for the top 300 meters is the y-axis. And this is now time. This is a depth time axis. So this is at a single point. It's a time series of all of the temperature and salinity data, and that point is the equator at 100 degrees west. So it's the central Pacific on the equator, and the salinity signal is quite interesting. You see a strong seasonal cycle. If you take the seasonal cycle out of the temperature field, what's left is a series of warm and cold events. These are the El Niños of 2006 here, 2009, and 2015. And as I said, these are heavily used data for both analysis and prediction of ENSO. I saved this, I guess, because ocean circulation is not obvious. It's obvious that you get ocean circulation at whatever is the parking depth of the Argo float. But the dynamics of ocean circulation is such that temperature and salinity will give you the vertical shear. So if you measure, but not the absolute, so if you measure the absolute velocity at one layer, and then you have the vertical shear, which is the change in velocity with depth, then you can get the velocity, the absolute velocity at any depth. So this is a global map by Allison Gray and Steve Reiser. This is the mean flow at 200 meters depth. The flow is along these contour lines. The flow speeds are something like 5 centimeters per second. These are the great ocean gyres. I mean, we've known of the existence of these things for a long time, but they've never been viewed with such a degree of accuracy as they are now. The Antarctic circumpolar current is clear here because you see the contour lines are crowded together, and the flow is from west to east. Here, the flow direction is clockwise in these northern hemisphere gyres, and it's anti-clockwise in the southern hemisphere gyres. And one of the things that Argo doesn't do terribly well is boundary currents, and there are western boundary currents on the western edges of all of these great gyres. I'm not saying Argo can't do boundary currents, but we need to accumulate a lot more data to resolve their fine spatial scales. So that's my story. I'm sticking to it. I think it's fair to say that Argo has greatly exceeded its initial goals, that observation of the global ocean is a reality, that the longer the program exists, the more valuable it's becoming. Climate time series gain greatly in value as they're extended in time. Data from the Argo program are finding many valuable applications in basic research, in operational oceanography, in climate assessment, in education and outreach. So it's very broad. The data set is extremely broad in its appeal. You can think of it as a facility that all oceanographers depend on at this point. The advances in float technology continue to be important, including increases in the float lifetime, as I showed you, and capabilities such as that for Deep Argo and BGC Argo. And Argo is a key element of the global ocean observing system, which includes many satellites and other in situ observational networks. And on behalf of Argo, I thank you for your attention.
Should we have time for some questions? As many of you know, we have a procedure for questions. We have mic runners with microphones that have foam, colored foam on top. So we have a red, a black, and a blue, and we're going to go in that order: red, black, blue, red, black, blue. Please hold your hand up long enough for the microphone runner to recognize you. They will eventually bring you a mic if you keep your hand up. When I call on you by your color, which is red, please stand, tell us your name, tell us if you're a member, and ask a question. Save the dialogue for the social hour. Thank you. Bob.
I'm Bob Hershey. I'm a member. How do the temperature rise figures in degrees per decade from Argo compare to some of the other measurements, such as by satellites?
So the satellite measurements are of the net heat. You can't convert them to directly to temperature trend. You can connect them to energy trend.
Okay.
There is not an accurate satellite estimate of the mean. So what I showed was that the variability tracks very well between the Argo data and the satellite data. The pre-Argo data has pretty large errors, a lot of scatter and differences between different analyses. But with Argo, I mean, this is the state of the art as far as measuring the heat accumulation in the climate system, and it seems to be in pretty good agreement with other estimates, but the others are not so accurate.
Black microphone. And the
name is
blue.
Frederica Derima. I'm a member. Thank you for your presentation. Very nice project. I have a question that's related in the sense that you pointed out that in the southern part, the southern hemisphere, the measurements are sparse, especially the importance of Antarctica and the changes in Antarctica. So are there any plans to increase the kind of measurements there? I know your project is using, a commercial kind of, is there any opportunity to increase these measurements? And also, in addition to that, in Greenland, for example, there are many more measurements. You talked about multidisciplinary kind of studies where atmospheric scientists are connecting with
Can you
your
hold the
data.
microphone up to your
Are
mouth?
connecting with your data to, in a sense, look at models that can, for example, address the effect of the rising temperature, let's say, in connection with the change of the sheets, the ice sheets in Greenland, and also what happens in Antarctica. And the other thing that you pointed out, the heat, of the ocean and the increase of the hurricanes, and are there studies now to use this data? Because we say, of course, we see many more hurricanes and more strong hurricanes because of the change in the temperature of the ocean, because we know that feeds the hurricane, the temperature of the water. Are there any models now that are using your data to do that?
Sure, let's take the last part of that first.
Can you repeat the question? Because I don't think it could be heard on the...
So I think there were basically two questions here, and the second one, which we'll take first, has to do with whether there are successful models taking advantage of Argo to look at phenomena like hurricane intensification and to predict it successfully. And yes, there are. And there's a quantity called tropical cyclone heat potential, I think. It was originally calculated from satellite altimeters because a lot of the signal in the altimeter is coming from that steric warming of the upper ocean, but now it's basically satellites and Argo, as well as if you have other instruments like XBTs. So yeah, there is a lot of interest in developing model applications, and both of the examples you mentioned, tropical cyclone heat potential and also the melting of high latitude ice sheets, those are all very active research lines of inquiry. The first question was, I guess, how are you going to fix that high latitude, high southern latitude dearth of observations? So we use all of the research vessels that are going to those high latitudes get used pretty heavily. It's not enough, partly because there aren't very many of them that go. They don't go often enough, and partly because there is I should now admit to you, there's a technology difficulty with sampling under the ice. So floats, by and large, were not deployed in seasonal ice for the early years of Argo. That's changed. Algorithms have been developed to detect whether there's ice above the float by looking at the temperature profile as it's collected. And so if the float says, oh, it's getting awfully cold here, I think it's freezing up above, it will stop and go back and basically initiate a new 10-day cycle without sending its data back. It'll save the data, it'll save it for a year or more if you like, and then eventually it'll send it back. But what's missing is, since it didn't surface, there's no GPS position with those data. So there is a challenge. I like to consider it a challenge for the modelers. You know, we do something for you, now you do something for us. Tell us how this pathway fills in.
Blue microphone somewhere? Yes.
Hello, my name is Matt Pfeiffer. I'm not a member. And I was wondering, what are the points of failure of the drones or the sensors? And when they do fail, do you collect them from the ocean? Do they just drift forever? Or what is that kind of timeline or process for the end of life?
So, okay, let me talk about first the the failure modes, if you will. For the float itself, I think in the early years we had relatively high failure rates. There were things like leaks or problems with the hydraulic system that would manifest themselves over the course of a few years, and that would basically kill the float after 3 or 4 years. Those have generally been solved, not entirely, but certainly by the more ambitious of the technology-oriented groups. And so we're getting much longer float lifetimes. We've extended the battery life of floats so that the floats that we deploy at Scripps have a battery life for about 12 to 14 years, rather than the old ones 3 to 4 years. So that's the first part of the answer to your other question, is that we can lower the environmental impact by building instruments that live longer. So then we don't need as many of them. It's not environmentally wise to go out and collect these things. It's perfectly possible to do so. I've recovered a number of them, but the environmental cost is greater than for leaving the float out there. It ends up mostly going back into the ocean over a course of years. It's aluminum, and I might say it's replaced so that that float, however many cycles it does, let's say 200, now it's replaced 200 expendable bathythermographs. It has a tiny fraction of the amount of metal that's in an XBT and a tiny fraction of the amount of plastic that's in an XBT. So it is not possible to carry out observations that have no environmental impact. As you know, just ships traveling across the ocean have considerable impact, but we can be sensitive to the impact, and certainly we work very hard to minimize it in the ways that I described.
We're going to go online and take the pink microphone, and then we'll do the red microphone, Carl.
So we have a question from Joel Wilson, who's a member watching from Maryland. Has there been any thought or consideration to use sonar to detect temperature gradients for deep sea?
Sure. There have been trial programs for a few decades looking at long-range acoustic propagation in order to deduce temperature change just by the change over time of how long it takes to transmit an acoustic pulse from one location to another that might be thousands of kilometers distant. It's a very interesting technology. It's pretty expensive. I think it's a more expensive way to measure the ocean than Argo is, but it's very attractive because it is, if you like, it's an integral measurement, and those have great value. And I think some of the engineering tests of that technology have been promising.
Red microphone, Carl. I'm sorry, red microphone, Carl.
Hi, Carl Merrill. I'm a member. I didn't hear any mention of any Navy program. This is all civilian. But I know during the Cold War, it was a big fuss used to be made about the importance of changes in the thermocline for hiding submarines, etc. And in that regard, I didn't see any data from Russia or China, which are pretty big countries. Is this all because of military problems or what?
Thank you for that non-controversial question, which I'm happy to answer. So you accurately noticed there were no Russian floats. We used to have a Russian Argo team. They somehow didn't manage to keep their funding stream going, and they sort of dropped off the map. There is a very active China program. There are, I don't know how many, do you know how many, Brian? How many Chinese floats are out there? About 100. So I think there are light green dots on that figure. We encourage all partners. We emphasize the peaceful uses of the data, but we understand that the navies are extremely interested in it for exactly the reasons that you mentioned. the U.S. Navy has its own float program. The floats that we know about put their data into the Argo data set. They're just another good partner in Argo. The floats we don't know about, we don't know about, so I have a hunch that, in places like the South China Sea, there could be quite a few floats that we don't know about. China's been pretty good up till now of producing data from the South China Sea, but that may be changing. So we're not totally immune from politics, but I think, we try to steer clear of the international sensitivities.
Black microphone?
Bryce Eldridge, I'm a member. How stationary do the Argo sensors, I mean, once you put them in and they keep surfacing and sending back, what's the drift factor? Do they tend to clump, disperse, move around? How does that work?
So that's a real interesting question. Thank you for bringing that up. It's so different in different parts of the ocean. So, for example, if you deploy a float on the equator, and it's feeling the 1,000-meter velocity, remember, not the surface velocity, but the 1,000-meter velocity. That float will go a couple thousand kilometers east for 6 months, and then it'll go a couple thousand kilometers west for 6 months, and then east, and then west. There's a huge sloshing at 1,000 meters in the Pacific Ocean of floats going zonally, but they don't disperse very much regionally. Other places like the mid-latitude, say the interior ocean gyres, the displacements are really very small. There's some random walk, but they pretty much stay where you deployed them. In the Southern Ocean, if they get into the ACC, they go like mad to the east. So there are places with strong mean circulations that do affect the floats, and others have very little mean circulation and don't have much effect. But here's the good news. There's not a large problem with clumping or gaps because the flow field at 1,000 meters is essentially non-divergent. That is not true at the sea surface. Surface drifters, for instance, deployed on the equator, get pushed off by Ekman transport. The wind-forced motion pushes them off the equator. That happened to Argo floats in the early days when we used a previous satellite communication system that required us to stay on the sea surface for 10 hours. But so those floats showed effects of surface divergence in their trajectory data. But then as soon as we switched to Iridium, 10 minutes on the sea surface, back down to 1,000 meters, and they just don't clump. And Brian can testify that I'm telling you the truth.
Isaac, you have the blue, and then we'll go to the red.
Hi, I'm Isaac Schomer, and I'm a member. And my question is, have you deployed any Argo floats on lakes? And the lake I'm most curious about is Lake Kivu in Africa, because it's a limnic lake which could explode CO2, and I'm wondering if the data from an Argo float could predict a potential explosion.
Argo might not know about it if the floats are deployed on lakes, because they'll have mission parameters that are sufficiently different from Argo floats that we're probably not going to give a lot of encouragement to get them into the Argo data set. There have been quite a few floats deployed in the Black Sea, so marginal seas, yes, not so much lakes that I'm aware of. Do you know of any, Brian? No?
They wouldn't be an RA system. Not every float is an Argo float.
Yep.
I think he wants to know whether something like an Argo float could be used to predict CO2-based explosion of a lake.
Well, there's no problem at all with deploying Argo floats in lakes, and you can give them whatever mission parameters you want. With Iridium, you can even change mission parameters on the fly, so you can tell it You can change the depth it descends to. You can change the frequency with which it cycles. You can change the sampling through the water column. There's a lot of free parameters there, and certainly the technology will work in lakes.
Okay, all right, well, thanks for that answer.
Red microphone?
Hi, I'm Kim Mahalik. I'm not a member yet, but hopefully I will be soon. I had a question following up about the biochemical aspect that you're going to be implementing on future Argo floats. You mentioned wanting to deploy those in low oxygen environments. What are some of the other parameters you're using to decide and prioritize where those new floats will go?
Beyond low oxygen environments. I mean, you know, the design for BGC Argo is to make it a global array. There are the priorities of the deploying countries are followed in the initial phases of a program, but then the idea is if you don't want to have quirky sampling of the ocean. You want to be able to sample it everywhere. It's distributed everywhere. In the case of BGC Argo, it's one float every 6 degrees by 6 degrees square, total of 1,000 BGC Argo floats. But I would say the initial interest is driving deployments in the oxygen minimum zones.
I think we're at the black microphone.
Adam Jacobson, I'm a member. When discussing Argo floats getting trapped under the ice, you mentioned that if they can't come up because of ice, they can't get a GPS fix on their position. Do Argo floats have any sort of backup inertial or other system to try to get an approximate position when they can't do GPS? And do they use GPS for keeping track of when they're making their observations, or do they use a different system for temporal resolution of the data?
Okay, I think there might have been more than one question there. Let's see if I remember them successfully. So there is a backup navigation system. The problem is it's very expensive. The backup is exactly what I showed you, the RAFOS, well, the inverted SOFAR float system can work with profiling floats. Our German colleagues have deployed sound sources in the Weddell Sea exactly for that purpose, so that they can follow the trajectories of floats in the Weddell even under ice. Now, the only catch is those floats still have to be able to make it to the sea surface during summertime some year, because they have to send back, they have to transmit all of their accumulated acoustic data. Now can I remember the second question? What was the second question?
Inertial navigation systems.
Well, yeah, I don't know about inertial, but as I said, I think the backup is acoustical. I'm not sure. I think inertial navigation has been considered. I don't think it's been looked at too hard. There were engineering problems on, I can't tell you exactly what they were. But what was your other?
The other question was timing. How do they know when they're recording data?
Okay, so yeah, I mean, as I said, they're only on the sea surface for 10 minutes. There's a GPS fix at the beginning of that 10 minutes and a GPS fix at the end. After that second GPS fix, the float immediately descends. It has timing information, but there's no GPS information, so we don't really know how much of a slant trajectory the float takes. But you know, typically over the 10-day cycle, if the float trajectory is, say, tens of kilometers, it's going to be a tiny fraction of that on the sea surface, and a very small fraction of that in drift as it goes down through the water column.
I think we're up to the blue microphone.
Hi,
Erin Jacqueline, I am not a member. I have two questions. One is, what kind of sampling frequencies are you doing? The second one is, can you explain a little bit more about the deep water? I'm assuming it's not coming back up to the surface all the time to give you data, and kind of what that looks like.
Okay, so the sensor, the CTD, is sampling at a rate of 1 hertz. And the float is descending, or in this case ascending, at something like 10 centimeters per second. So that's the vertical resolution of the raw data is about 10 centimeters. We typically don't send all of that, the raw data set, back. We usually average over bins that might be 1 or 2 meters thick. So we're averaging 10 or 20 discrete measurements. Many of our groups send back some of the raw data, but typically we don't want to use so much iridium bandwidth as to send back the entire profile. And most of the uses, most of the applications are very happy with the sort of 1 or 2 decibar resolution. If there was a big demand for doing better than that, I think we'd listen carefully. I hate these two-part questions because I can never...
Sorry, the second one was, can you explain a little bit more about the deep water systems?
Well, it follows really the same mission as the upper ocean Argo float. So the only difference being at least the float that we've built at Scripps samples on the way down rather than on the way up for technical reasons. But it's going all the way to the ocean bottom. The engineers were very clever. We didn't want it crashing into the ocean bottom, especially with the CTD on the bottom like it is. So there's a 3-meter length of stainless wire hanging below the float. And when you lay about 1 meter of that wire on the bottom, the rest of the float becomes neutrally buoyant and stops dropping. So the buoyancy is controlled with a lot of precision to be able to make it do that sort of very soft landing, moving very slowly when you get down close to the bottom and then stopping before you run into the mud. And then it returns to the sea surface on every cycle, just as the upper ocean float does. So there's more energy needed for buoyancy control in the deep float, as you can well imagine. It's roughly 3 times as much per profile, but we can still get between 200 and 250 cycles to 6,000 meters out of a deep Argo float. So that's, if they're every 10 days, I don't know, what's that, 6 or 7 years?
Red, then black, and we have another question over here, and I think we're going to be winding down on the questioning.
I'm Barry Vienna. I'm not yet a member, but I'm waiting with great trepidation to see if I'm accepted.
You just applied today.
What is the annual budget for this program, and what percentage does the U.S. government pay for?
I can only partly answer that. I know the U.S. contribution in FY19, it was $10.8 million. The U.S. does...
Bargain.
I think it's a great bargain, and that works out to $200 per profile. All nations, that's pretty much of an all-inclusive, except it doesn't include very much research. We're kind of on our own to get money to analyze Argo data. Other nations operate with different definitions of what they package together in their Argo program, and we typically don't know what their annual budget is. But we know that the U.S. is doing half of the global array, so a rough guess would be that the other half of the global array costs about the same if we were to just compare apples with apples.
Black microphone.
Yes, hello, I'm Charlie Hutner. I am a member, and I'm also a former Air Force pilot that flew C-141 cargo ships down to McMurdo Sound. And I know that routinely there are Air Force aircraft that go down to our research station there. Have you ever thought about airdropping hundreds of these sensors in an area that you really need them?
Yes, and it wouldn't be nice if I quit there, would it? Yes, and there is ongoing air deployment of Argo floats under various conditions. I don't know that. I don't know of deployments on that particular flight path, but for instance, the NOAA hurricane hunters deploy Argo floats or Argo-like floats in front of North Atlantic hurricanes. You can't. So there are also research vessel transits to the Antarctic at several locations. So, and one of them happens to be pretty much south from New Zealand. So we have almost yearly availability of ship tracks along there. This,
What I'm suggesting is...
You don't have a microphone, so.
What I'm suggesting is McMurdo is a scientific station. You could have a C-130 deploy from there and go anywhere you want it to go, and the back door opens up and you can airdrop things right out of it. I would think the Air Force might be helpful in this case.
You might like to discuss that after at the social hour. Perhaps you have a good contact.
It has been thought through, but the range of a C-130 is not that great, in my understanding. I mean, how far can...
Let's save the discussion for later, really.
Hi, I'm Elisa Wynn. I'm the guest of a member. Since your system is open source, I'm interested in what kind of feedback, how do you know who's using, in particular, as an example, like your pH data and people who might be doing ocean acidification studies. How do you hear back? Do they, I know you had your papers published in that, you can look for that, but how do you know the impact of your data?
That's a really good question, and it's a really hard problem. And the reason I'm here in Washington this week, we had a 5-yearly review of the U.S. Argo program. Brian King was the chair of the review committee. Maybe you should ask him this question, but the answer is we get this every time there's a review. You need to work harder to identify your user community and find out what their needs are, and I agree with that. But if you've got some better ideas than I have, I'd like to hear them.
I want to get this on the video.
We try to track all of the applications of Argo data. So there's a complete bibliography. It's got 3,800 published papers in it. We look at what those papers are used for. So far, there's the list of PhD theses. There are over 300 PhD theses using Argo data. We track all of the operational centers that we know of that ingest Argo data and what they use it for. So we do everything we can think of to track what the applications are, but it's very difficult. The observation community and the modeling community are both very, very busy. There are some great modeling projects that are more or less descendant. I told you that the Global Ocean Data Assimilation Experiment helped get Argo started. It has descendant programs that are still very useful for us to interact with, but every 5 years we hear this again. We need to do better connecting with user communities.
So I think we'll wrap up the formal question and answer period at this point, but there is a social hour afterwards, and you can grab the speaker and ask questions and continue your discussion about cargo planes and McMurdo. at the social hour. Before we go, I'd like to present our speaker with a gift.
Thank you all for
So an appreciation for coming from beautiful San Diego to dismal DC. I have this couple of gifts here. One is Volume 1 of the Philosophical Society of Washington, which is the minutes of the society, including the founding minutes from March 1871 to June 1874. And it might be interesting to you because there are a few oceanographers in here before oceanography was oceanography. And also a framed copy of the announcement of your talk signed by all of the members of the General Committee on behalf of the membership. So thank you very, very much for coming and joining us here and telling us about Argo.
Thank you, Larry.
Before we go, we have the usual suite of closing announcements. PSW is a 501c3 nonprofit organization, tax exempt under Section 501c3 of the Internal Revenue Code, and contributions are tax deductible to the extent permitted by law in the current administration and the next one. All PSW members in good standing may wear the PSW rosette, and if you wish to purchase one, you may do so at the rosette table at the back of the auditorium. Please keep in mind that PSW depends on members and sponsors. We're all volunteers here. Nobody's getting paid to do this stuff. If you are a member and you haven't paid your 2019-2020 dues, please do so. And whether you have paid your dues or you have not paid your dues, please consider making an additional donation, sponsoring a lecture series, or volunteering to help carry out the Society's activities. If you're not a member, and I think there are a few people who said they're not and they're planning to join, please join. You can apply for membership via the PSW website. I won't belabor it. There's a join button on the home page, and it pulls up this page, which gives you a link to the membership application form, which you can fill out, and when you get to the end, you submit your application form. If you haven't filled out all of the mandatory fields, it will reject you and say, please fill out the missing information. It will then ask you to pay. You can pay with any credit card you want. And if your membership application will be considered, and you should receive in due course your admission to membership in the Society. If you have any questions, please see Membership Director Lloyd Mitchell, who is standing at the back of the room, or Corresponding Secretary Robin Taylor, who is ensconced behind the audio rack because she's also doing duty as our live stream director. Our next lecture will be the 2,417th meeting of the Society. It will be held here in the Powell Auditorium December 6, 2019. The speaker will be Harold Hess. He is group leader at the Howard Hughes Medical Institute, Genelia Farms campus. Harold will be speaking on super resolution and 3D imaging, brain circuits to cell ultrastructures, transforming views of biology with innovative microscopes. Harold's lecture is sponsored by PSW Science member Tim Thomas. Harold is the close colleague and collaborator of Eric Betzig, who won the Nobel Prize not too long ago for work on super resolution microscopy. The January 10th lecture remains to be determined. Our mystery guest will be announced in due course. On January 24th, at the 2019 meeting, we'll have Ellen Stofan, the Adrian Mars Director of the Smithsonian's National Air and Space Museum, giving a lecture on Venus. Venus is of increasing interest to the space exploration community as being a model of how planets evolve into being very, very, very hot, for obvious reasons. On February 7th, 2020, the 2,420th meeting, we'll have a lecture by Jack Gilbert who is a professor in the Department of Pediatrics and a professor at the Scripps Institution of Oceanography, who's going to be talking about the World Microbiome Project and integrated microbiomics. On February 21st, the 2,241st lecture will be the annual President's Formal Dinner and Lecture, and the speaker will be Joachim Frank. He is professor of biochemistry and molecular biophysics and of biological sciences at Columbia University. He is also distinguished professor of the State University of New York at Albany. He is the inventor and developer of single-particle cryo-electron microscopy and methods for cryo-electron microscopy determination of molecular structures at atomic resolution. He was awarded the 2017 Nobel Prize in Chemistry for this work together with Jacques Dubochet and Richard Henderson, and he will be speaking on single-particle cryo-electron microscopy, revolutionary methods for determining molecular structure. The lecture is sponsored by Millen White, Solano, and Brannigan. The 2,422nd lecture will be on March 6, 2020. The speaker will be Rajesh Rao, who is the Chern Jia and Elizabeth Yun Wang Professor and Director of Neural Systems Laboratory in the Department of Electrical and Computer Engineering at the University of Washington, Seattle, and he will be speaking on brain-computer interfaces. And then the 2,423rd meeting will be on March 20th, 2020, and the speaker will be Henrik Christensen, who is Professor of Engineering and the Director of the Contextual Robotics Institute at UCSD. The lecture is sponsored by PSW Science member Erica Kane. Thank you, Erica. And he will be speaking on robotics. And the last I'll mention is that on May 15th, Shep Dolman will be speaking on the Event Horizon Telescope Consortium, which not long ago took the first picture of a black hole. The schedule will be filled in, and you can check the website, or you should check the website periodically to keep up to date. I would like to thank tonight's crew. So James Heelan, who read the minutes, Savannah Crawford, who was the room manager, took care of the live chat and is at the Rosette table. Robin Taylor, who did the video setup and breakdown, live stream, and serves as video director. Brett Magaram and Connor Nixon, who ran the cameras. Our red, white, and blue mic runners. And our post-lecture wrangler, Lloyd Mitchell. Thank you all very much. The social hour ends promptly at 10:30. Please use the side entrance to exit the building, the side exit to exit the building. I will now accept a motion for adjournment of the 2,416th meeting of the Society to the Social Hour. Second. All members in favor? All members opposed? The meeting is adjourned to the social hour. Thank you all for attending.